So I'm going to share a brief 3.5-minute interpreters versus compilers video to start the class, because I feel like we need a little bit of breakup of the monotony of talking about LR parsing from yesterday. That was a bit intense. We'll get back to it after this, but I revealed the last assignment. That's up. The plan is to get the LL up after class. There is one mistake in the output file that I needed to fix before publishing it. So it's in the process of being edited, and then I ran out of my office right as I was about to upload it and publish it. So it should be up right after class. You'll know everything that you need to do between now and the end of the quarter at that point. Any other questions before we dive into a fun retro styled difference between interpreters and compilers? I love this video. It's really funny to me. If I could live on planet Gobbledygook, I would. We have sound. Audio is up here. Audio is up here. You think you do everything. Yeah. Just the room that hates me. Wonder if I would turn the room off and on again. Usually what the problem is. Have sound. We don't. Well,
You just like play it off your laptop and hold it up like this.
Can you switch the speaker to your laptop speaker and just turn it up really high?
yeah, what I'm gonna have to do.
You're thinking about it?
You just turn on subtitles.
The issue is
Is it up on YouTube?
listed on YouTube.
It's your own production.
It was working earlier this quarter. This is literally what I did earlier this quarter.
Yeah.
See if we get something now. All right, so we will have to do it through my laptop speakers. Can people hear this?
Don't turn on subtitles.
Sorry,
Subtitles. Sync.
should be. Is they on? Are they on?
Well, it might be in Spanish. So.
Speaking Spanish.
Actually, people will make subtitles for the language.
All right, let's do it. We're ready. We can do this.
When you landed the world of computers with a strange, convoluted machine language, it's a bit like landing on another planet, whose inhabitants speak an equally strange, convoluted alien language. Getting a mechanic on planet Gobbledygook to repair your spaceship would present the same sort of problem that you have when you want to get a computer to do something. Everything you say has to be translated. And you have a choice between two different sorts of translator. One of them is called an interpreter, and the other is called a compiler. Let's suppose that you've previously written out your list of instructions for the repair of your spaceship. And suppose that you choose the interpreter to do the translating. He reads your first instruction. Open lid of rocket engine. Translates this into gobbledygook. Immediately passes it on to the mechanic, who executes the instruction. Then the interpreter reads your second instruction. Remove spark plug. Translates this into gobbledygook and passes it on to the mechanic, who executes it. And so on and so forth. Now, notice how the interpreter works. He stays with you all the time, and he translates each of your instructions immediately, one by one. This is a rapid process, because the mechanic has to wait while each instruction is being translated. But, on the other hand, it does give you a chance to correct your mistakes as you go along. If the mechanic removes the wrong spark plug, for instance, you'll see this happen right away, and you'll be able to change your instruction accordingly. It's the way the second sort of translator, the compiler, goes about his work. He takes your complete list of instructions, and without further ado, translates the whole lot straight into gobbledygook. He then hands them back to you and goes away, leaving you all on your own. All this has taken some time, but from now on, things will go very fast. You hand the complete list of gobbledygook to the mechanic, and he executes them all in one go. Bang, bang, bang. There's no waiting about this time. But there's one disadvantage to this, of course. If there was a mistake in your instructions, it's too late. This analogy comes very close to the way the interpreter and compiler translator programs actually work with computers. An interpreter runs slowly, starts right away, and lets you see how things are going. Whereas a compiler takes extra preparation time before your program can run, but then lets it run very quickly, efficiently. To help you remember the difference between an interpreter and a compiler, look at the words themselves. Inter means between. The interpreter is always between your program and the computer, and it translates line by line. To compile, on the other hand, means to pile together. A compiler piles together your entire program and translates the whole thing all at once. Which one you use on Planet Gobbledygook is entirely up to you.
Excellent. So I thought I'd share that. I share that in a couple of the classes that I teach because it becomes relevant when you're talking about things like, is this language compiled or interpreted? And languages aren't compiled or interpreted. You write a compiler or an interpreter for a particular language. And some language strengths lend themselves really well to one or the other, and et cetera. So there's nothing preventing you from writing a Python compiler, even though it is typically interpreted, because it is a scripting language. It is meant for you to be able to write line at a time and execute line at a time, watching what you are doing as you go. Whereas a language like C that is built for efficiency is typically compiled. You could write an interpreter for C, but it goes against the foundations of C being efficiency oriented. And an interpreter is slow. It's interpreting everything one instruction at a time as you're writing it. And C programs are usually meant for embedded systems, something where you don't really have that level of user instruction writing and interpreting running at that time. So nothing about languages, more of design decisions about how to translate the higher level language down to whatever that middle language assembly bytecode is. Questions on that idea? So maybe you've seen some of those before. Maybe you've worked with interpreters, maybe you've worked with compilers, but that video summarizes it really well as to what the advantages and disadvantages to each of them are. Some languages have both interpreters and compilers written for them. And which one you use is up to what you're using it for. All right, I killed 12 minutes of class with something useful. Excellent. Now we can get back to hopefully finishing this up today. That's my goal. So last class, we introduced the concept of LR parsing, which was not at all like LL parsing. We needed a lot more going on. So let's actually just quickly go through that idea real quick. So we said we're using the same grammar that we were using, and we wanted to model the LR, kind of a bottom-up process. So all of our work is now being done in Q0 as we either have shifted enough symbols and found something that matches to the right-hand side of a production. We can do a reduce. A reduce takes the right-hand side of a production and replaces it with the left-hand side of a production. We are starting with the string and trying to produce the start non-terminal. From there, once we only have the start non-terminal on the stack, we can go to Q1, removing the start non-terminal, and then to Q2, removing the bottom of stack symbol to accept. So there were two different types. We talked about the reduce. The shift is just taking a character from the input string and putting it on the stack. We ended up saying that this is basically non-deterministic, whether we shift or reduce when both of them are possible. And we needed some kind of algorithm to remove that non-determinism so that we can tackle this problem deterministically. Just like with LL, we need to know whether to shift or reduce. We need some algorithm that helps us with that. We gave an example. That was the exact same example we've been using. So just like with LL, we have a stack history, we store the look ahead character, but now we can take the string, we can start shifting characters from the string onto the stack. Once we have the stack at a position where we can replace the right-hand side of a production with its left-hand side, like this C is the right-hand side of a production, A arrow C. So we can do a reduce and change the C into an A. Now what's on the stack is this B capital AA, which maps the right-hand side of that production. We can now reduce that to just be an A, continue to, or actually we need to reduce the A to an S before we shift on the B, reduce this to an S and go to accept. There were two big issues. The first was the non-determinism that we mentioned. The second was that we needed to dig deep down into this stack, and we can't look at elements below the first element on the stack. So we needed some way to store what was on the stack in a way that scales. We could just store the stack as a list to parse that list. But since we don't know the size of that stack, that could require an arbitrarily large amount of memory. So that is why we introduced the concept of items enclosure. This is going to give us a way to use a finite amount of memory to actually know what's on the stack when we have the ability to reduce. So the first idea was items are just being the production's closure is now this concept of you're going to make the production with a marker in it. A marker is just this dot. And that tells us that everything to the left of this dot is currently on the stack. Everything to the right of it is not yet on the stack. And now we just use the finite size of the grammar to be able to tell us what's on the stack or not on the stack. Even if there's an infinite or nearly infinite amount of material on the stack, we only need to store the items enclosure from the grammar so it does scale. So we went through an example closure. We said that given this context-free grammar, we wanted to calculate the closure of a.sb. And a closure was just everything that could be on the stack in order for us to move the dot past the S. To say now this S is on the stack. But we need to know all the possible reductions that we could see on the stack to be able to manipulate, reduce, get that S on the stack so that we could move past it in this closure. So this process, you start by setting the closure to itself. And then we go into a loop, trying to figure out, okay, what right-hand sides could exist such that if we saw the marker at the end of that right-hand side, then we could reduce it down to an S. So we're going to do that. Here are the two productions that say basically, if this item ever becomes, this marker ever gets to the end, then we can reduce these symbols now down to an S, which we can now move past. Same thing with this dot A. If we now get the A on the stack, then we could reduce the A back to an S and then move past this S in this closure. Since there was an element that we added to this closure that was before a non-terminal, we need to loop this for every possible production that A can go to. So we add a couple more elements. Since A can go to B capital A C or just C, we start with the item on the full left-hand side of this. If we ever get all the way to the end of one of these, saying this is now all on the stack, then we could reduce all of this to an A, reduce the A to an S, and then move past it in this closure. Since we added no more new elements, the loop terminates, and now this closure is complete. So this just tells us everything that we could see from here. If we added this all to the stack from this moment, then we would be able to reduce this and move past this S in this initial closure. Were there any questions on that? That was kind of a brief review of that, but anything I can address before we move on and see a full example of an LR parse? All right. So there's the marker to the left of an item. This is the last slide we were on. We said, this is just summarizing what I already just said. We now have a shift operation from here, placing an A on the stack. We can reduce to an S for something that eventually allows us to move past that S. And then we move past it. So this is basically what I just described with, you can, from any element of that closure, fill that closure, reduce to that non-terminal, and then move past that non-terminal in order to now attempt to eventually map to the end of that closure. All of this is meant to just derive the start non-terminal eventually. This turns out to have relevance to regular languages because we are actually going to build a DFA of closures. And the DFA of closures is going to allow us to determine when to shift versus reduce. So here is the DFA algorithm for this, but let's at least talk about it a little bit. So we can now complete LR, assuming that we can look multiple positions down the stack, which we can't do. So we need to build this DFA that tells us which transitions we can take between the closures that will eventually backtrack to allow us to be able to have stored the relevant history for each closure. I think that requires an example. But for each state in the DFA, we're going to be having an association with some number of items in the grammar with their associated marker that tells us which are on the stack, which are not yet on the stack, and then transitions within that DFA will be on characters in the string. On those characters in the string, we will either be changing where the items are in the associated closures that we're sticking around with and caring about. So as we parse a string, we go through the DFA, and we really need an example for this. So I will come back to this algorithm after we do this example. So here it is, we're going to, as this algorithm would state, it says to add a new start state, compute the closure of now this concept of S prime, this new start state. And this will become necessary as we see exactly what this does when we walk through the example. So new start symbol, S prime, new production, S prime, arrow S. This does literally nothing aside from notationally allow us to work with this. We will then number the productions. So here is the grammar with the productions numbered. Start with the S prime arrow S as production 0, and then just go number them from there. The first 2 S productions will get the numbers 1 and 2. The last 2 will get 3 and 4 for the A's. We're going to create a start state called Q0. We're going to call that state 0. Then we calculate the closure of S prime arrow S. So since it starts with a non-terminal, we need to add in every element that S can go to on the right-hand side. So we're going to add the marker to the left-hand side of this and that. And since this item here has the marker before a non-terminal, we again have to loop and add everything that A can. So this is the closure of S prime arrow S. And we're going to associate this set with this state 0. Saying that if we ever get back to this state, somehow with a marker being on the far right-hand side, we can reduce to S and go past that S. If state 0, if all that was done there is the very first thing of, we can now with that have an empty stack after we get rid of that S, we would have been able to say, yes, this string is in this language. So the visual for this would look something like this. We're going to attach a list or a set really of items with their associated markers to this Q0. The closure of S prime arrow S is now attached to Q0. We now need to go into a loop and expand states. So each of these elements that are associated with it creates a transition out of it, where it's going to do something with the next character in it. So for the S prime arrow S, the marker becomes over S to create the new item S prime arrow S dot. Closure of this adds nothing. So we create a new state 1 and associate the item S prime arrow S dot with that new state 1. This is going to be the acceptance state, that once we've moved past this S, then we have found the S that this all, since this is the very first S in the grammar, once we can move past this very first S, we have completed the whole process of finding a string, reducing it all the way down to the start non-terminal, which we can then move past. So this is working its way toward finality. For this item, S arrow A capital SB, we can move the marker over the A to make this item we then look at the closure of that, generate the closure of that, create state 2 and associate this set with that state. Basically, if we see an A, if we read an A in the string, we would move past that A, saying that we would shift this onto the stack. And then if we could find this SB somewhere in what is to come, we could reduce this down to that and move past this S. If we got all the way to the end of A.SB, we could reduce this back to the S, back to state 0. We'll see how that works momentarily. Continue this process for the 3 remaining states so that we have 5 states associated with it, and you get this. We end up with 5 states and their associated closures. So to further describe this S prime arrow dot S, we move it past the S and we get here. We move it past the A and we get, where did that end up? Here on a lowercase a. If we can move past a capital A, then on a transition of a capital A, we could get to here. On a transition of a C, we could get here, moving the item, the marker past C. And on a lowercase b, we could move the marker past there and generate that closure. So all you're doing is in a loop generating the closure of taking every item in this closure and moving the marker one space past. Generating the closure of all of those and associating them with new states. Questions on this process so far? We look dead again. We were excited for compilers and interpreters, and now we have reached the dead state. Question?
For state 4, on the B, we moved the mark for the first production of A, but not the second.
Yes, because when you move this marker past, so this is saying we found the B for this BAA. We found this B, but when we move past this, there's a non-terminal that starts this, so we need to add everything to the closure of that capital A. So the A could go into B capital AA. So this could be something like, if we saw, what would this be like? This. If we had something like this, if the B were on the stack and we were at this position, there's a marker right there in this, the B is on the stack. This B is also on the stack, but to be able to move past this A, we would need to be able to generate this B capital AA, which is what this B capital AA would represent, is the A in this A that could then, we could reduce this down to that A and then this down to this B A that's down here, basically. We could move past this A here once we had seen the definition of an A in the middle of that string. Does that answer the question or make sense?
Each of these associations are the closures of the top production.
Yeah, of this. So we start with this kind of dummy S prime arrow dot S, which means that we need to now add the closure of S into this initial state. And that gives us a way to now iterate and loop forward into producing the rest of these. Of course, this is only part way because we now need to recursively or loop this for every state that's there until the CFA is complete. Yeah.
For Q2, why are there all 5 of them?
So when we have, by moving here, we're following this S arrow ASB. We're saying that if we shifted the A onto the stack, which is this transition here, then we end up with A dot SB. Since a non-terminal appears to the right of this, we need to add everything from the closure of S. So every production that we could get to, which generates this and that. And since this one now has a non-terminal to the right-hand side of that, we add this and that.
That makes sense, thank you.
Yeah,
I was just saying the first,
the first,
like for like the first table, or is that, what are the edges mean again?
the transitions. So basically for every element of this set, the transition would be, if we can find a way now to move past this symbol. If we could now reduce something to now get at this S, how could we do that? There are a bunch of different ways to be able to move past this S. We could see a single C, we could shift a single C onto it, which now reduces to an A, which would then move forward here. And since we have an A that can become an S, we could then reduce that here and move forward in this S. So this defines all of the possible different stack configurations that would allow us to move past this S. And then some of these lead to some other places, lead to some other places, lead to some other places. But the idea is eventually we would know that there is some sequence of symbols on the stack that can be reduced in some capacity to get us to that S that we can move past. One of the two.
What would the final state be? Or is there no final state for this?
It's gonna be moving to here, once we move past this initial S, when we have this S prime arrow dot S. If we can move past this S, this would signify that we have found a way to reduce this string down into a single S that we can move past. So this Q1 will be the first position of leading to acceptance. We'll see that at the very end, but it's something right off of this.
Rejection for this would be like if the next character isn't part of the first.
Yeah.
Of this set.
Yeah, if we can't do anything, and we'll see that as this is a DFA and not an NFA, we will actually have similarly sized or similar trap states to, if you read this, go somewhere and we have to reject from there. Other questions? All great questions.
We're gonna run with these on my test.
LR is not on an exam. I am mostly stopping with content with LL because it's doable. LR is pretty gross, and if I threw something like this on an exam, it's really hard to come up with a simple enough example that even something like this with 4 productions is gonna balloon from here into lots of states. And I could not throw something like that on an exam without making it the entire exam. And I don't want a fourth of your class's exam to be based on your understanding of this process.
Optional third project stuff.
Yeah, you could, honestly, in being able to do this it's a cool project. It's a really cool project that just I've never had time for. And I just don't think fits in the scope of a 10-week course. But I think it's also important to know how to do this because as mentioned earlier, there are some grammars that are LR that aren't LL. So you can efficiently parse faster than CYK some grammars that you might want to. And you might need to use this form for. Of course, if you can use LL, you probably should. It's a lot simpler. But there are some grammars that need this in order to be able to be efficiently parsed. All right, continuing. We now need a queue for each of these states. We're going to add all of these states to a queue, saying we're going to expand each of these states, but we don't need to expand anything with a single element. So looking back at here we have Q1, Q3, and Q5. They just don't have, there's nothing to expand here. We've already moved past the right-hand side and nothing was added to that closure of that state. So we just we don't need more work. But Q2 and Q4, on the other hand, have multiple elements associated with them. So we are going to need to expand them. So we're going to move past every single symbol in each one of those, creating new sets. However, some of those sets may map to exactly the sets of states that we've already seen. If that is the case, then we just have a transition back to an existing state. If they have an exact item set that's exactly the same as an existing set. So expanding state 2 creates 5 more states. But some of those states have the same sets as existing states, so their transitions lead to existing states. And we continue doing this until there are no more unvisited states. So you add everything to a queue, find the set of that, see if it exists. If it exists, transition to that state on that first character. Otherwise, make a new state with the new closure of that. And we end up with this. Like I said, it's kind of gross. And we find that some states end up being final if we can backtrack from those states back to Q0 and move past S to get to there. So Q1 ends up being final, and a lot of these other states also end up being final. Because, like for instance here, S arrow ASB, to get there, we had to put the A, the S, and the B on the stack. So when we get here, we could backtrack through the B, the S, and the A, move past this S, and transition to Q1. So rather than defining all of that logic, we just make Q8 final, saying that if this is what's on the stack at this point, we can just stop and accept. because it's a DFA, it doesn't adhere to the NPDA rules where you have to be in the final state at the end of the string with an empty stack. It's a DFA. So you can just accept at that point. So let's take a look at an example of how this might be done. I wish I had the grammar here. We had, I guess I can reconstruct it. We have S arrow ASB or A. We had A arrow BAA or C. Let's find a string in this language that we can actually go through and check. Someone come up with one. Preferably not one that's the same one that we've been using.
ACB.
ACB. And we get there by S arrow ASB, arrow AAB, arrow ACB. That'll work. So we would start here with the string ACB. And now we want to see, all right, we want to make a transition on this DFA that consumes the A. So we can do that. But we consume this A going to Q2. From Q2, we're kind of at the, all right, we've seen the A, so we're kind of at this position. But all of the different ways that we could resolve this S are here. So what is the next character that we want to get? We want to see if C is there. So is there anything here that consumes a C? Yes, this one. A arrow dot C. So we're going to transition from here, consuming the C, out to Q5. We're past this C, and what's on the stack now is we basically did a shift of the, A, we did a shift of the C. Now we're here. This tells us that we can reduce the C to an A. So we can pop off the C, replace it with an A, backtrack from Q5 back to Q2 where we came from, consume the A. This tells us that this can now become an S because we can now backtrack from here and consume that S. So this A can now become an S. And we move past the S that was here so now that we have an S on the stack, we can take that transition since that's what's on top of the stack. So we take this transition going to Q6. Moving past this S, we're now looking for a B. So we shift the B onto the stack. Moving here, and then we can see that we're in an accepting state at the right-hand side. So we know that this ASB is on the stack, and that by removing everything from here, we can just even go backwards from everywhere that we came. So we pop the B, so we take the inverse of the B transition going into this state, pop off the S, inverse S, pop off the A, inverse A, move past this S, move here to accept. So that is one example of how to read and use this DFA. But it's a lot. Question?
Can you talk about like the self loop? Like what would be an example of? What is
Yeah,
that self loop kind of?
That self loop is coming from the fact that this A, if you can consume a B, you can recurse this definition of an A. So if you had something like, let's see, S arrow A arrow B A arrow B B A arrow B B B A arrow B B B C A, something like this. Once you reach here, you can continue to consume a B and then have to resolve this A. As part of this A's definition, consume a B, have to resolve another A. Consume a B, have to resolve another A. So it's a loop to itself in that when you consume this A, or sorry, consume this B, what becomes part of that closure is exactly this set. The closure of this A is what this set is defining. So it becomes a self loop. Self loops are much rarer. But you can see another one here where A, S, B, we define S in terms of a terminal followed by that same non-terminal. Whenever you see that behavior, there will be a self loop. How are we doing? Does that make sense? Sometimes I have a hard time telling if a description has been good enough to help to understand this. How are we feeling about this? So if we can build this DFA, then we can actually go through an LR parse. So I'm going to go through an example of this in more detail. Again, I wanted to come up with one and do it ourselves, but now I can also make the full stack example and give you that. So we'll give you an example LR1 parse. A lot more needed to build an LR1 table. We need all of this. So starting at the DFA start state, we are going to continue to apply shift and reduce operations until we reach just the S on top of the stack. Start symbol is on top of the stack. Shifts move the DFA forward, reduces will go backwards for every symbol and then forwards. So using the current symbol in the input string, follow the transition on that symbol from the current state in the DFA, pushing that symbol on the stack. So an example of that is like we see this lowercase a, that's a shift moving past this A. We're going to take the A from the string, move it onto the stack, and take this transition to move past this A. So that represents a shift. A reduce goes backwards on the DFA for each symbol on the right-hand side, then forward from the non-terminal. So an example of this would be something like, if we were going to reduce we did this when we did the A arrow C here. So we moved to the C, moved past the C, and now we can follow this transition in reverse for every symbol on the right-hand side, and then move forward on the capital A to move past that A. If it were more complicated than that, let's do the BAA. So here's an example where we shifted the B, made the A, shifted the A. Now we have this position. If we wanted to do this reduce, we would follow backwards, the A, the capital A, the B, and then forwards on the A. So that's how a shift and a reduce are embedded within this DFA.
So the backtrack doesn't require an arrow to go back?
Yeah, you would follow the arrow. Since in this particular DFA, we can't have multiple arrows with the same symbol going into the same state. There is a unique transition. So you have to define kind of the reverse transition object to say what transitions lead into this object on that symbol. And there's only going to be one of them, but then you would follow that transition in reverse. So if the item is in a final state, then we can do a reduce. We can move all the way backwards and forwards like we do. Backtracking, if the production has n symbols on its right-hand side, then we move that many symbols backwards before we move a single forwards that is the left-hand side of that. Then just do the same thing to the stack. That's going to represent the same stack symbols that we are using. As we traverse backwards, every backwards one is popping something off the stack. Everything forwards is pushing something on the stack. So before, if we had a stack that had something like an ASB like that, if we were going backwards from that state, so from here to here, that got rid of this B, we would pop that, we would go backwards to something else, pop that, backwards to something else, pop that, and then forwards to something else. Not a triangle. Forwards and something else that would put the S that was the left-hand side of that production back on the stack. So backwards, 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 forwards. Backwards on the B pops it, backwards on the S pops it, backwards on the A pops it. The S is now pushed on the stack because the item at this point would have been something like an a BSA dot. So then we would go backwards. What would be here would be the BS dot A. Backwards one more would be the, sorry, this should be here. B dot SA. BS dot A here. S dot A. B dot SA. Dot BSA. We go all the way through that, and then this would also have the dot S, where this would be the S dot. So we go all the way backwards to be able to move forwards from this S because of the S arrow ASB. Sorry, I completely flipped that. ASB. Need more coffee. Dot ASB. By resolving all of that, then we can move forward past this S in this forward transition. Sorry, that was way too messy. But it works. From this final state, backwards, 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 pop, pop, pop. Through the B, through the S, through the A, forwards through the S. Does that make sense? I apologize for kind of losing my mind halfway through that. But that's correct. So that's how we read and manipulate the diagram. Full example of this using the same string, same grammar, same ABCAB. I wanted something else to work with before knowing this was coming. You would say something like, all right, we're going to include the state as well, because sometimes we would need to know which state we are coming from. So these are kind of pairs that we see on the stack. This A2, this B4, this C5 are that. So we would see which state we're in, which look ahead is the next character that we're using, and action being a shift or a reduce. So from state 0, we're going to push on the fact that the next symbol that we needed to see, we're going to shift on the A. By shifting on the A, we transition from state 0 to state 2. The next thing we do is to shift on the B. Since the look ahead is a B, we look at every item there and see, is there something we can do with a B? If there is, we go do it. Same thing with a C, we go to 5, and now we can start reducing. The C5 gives us the A. So we backtrack from state 5 back to state 4, popping this, and we move forward from state 4 to state 7. I feel like I have to have this right next to it in order to show it. So we move from 0 to 2 here. We move from 2 to 4 on the B. And then we move from 4 to 7, consuming this A after we had found that we could get there by consuming this C. So we went backwards, forwards, past the C, backwards, and now we can move past this A here. Out of time. We'll continue to go through this. Here's kind of an English description of exactly what's happening as we do it, but I'll go through this in more detail at the start of tomorrow's class. Plan for tomorrow will be there's not much left here. There's this and one more slide, and then that's all of the content for LR parsing. I will introduce you some practice problems for getting started studying for exam 3 and get out a study guide for exam 3. So that's the plan for tomorrow. I'll see you for that. Question?
Can you reveal the L1?
Yes, yeah, I'm gonna go to my office and reveal the LL project.
There's one total left, 2 exams left, and the CYK algorithm.
CYK algorithm and the LL algorithm.
One
Yeah.
homework, 2 exam, 2 project.
Yeah.
All the closing meetings.
There is technically a final, but you will have the ability to either take that the Friday of week 10 or the Monday of finals. So our technical final slot is that Monday, but I will. That Friday class will be optional. If you come, there will be an exam to take so that you can focus on other classes, do something else. If you need to get out of here, go home for the summer, something like that.
You're gonna take the higher score.
It's gonna be the same exam. That would be interesting. Take it, go home, study, come back. No, you'll have to choose one of the two.
I'm so glad I made that Turing
Are you gonna go
machine
for
like interpreter
Got it.
because I was using it on the homework and